So I'm using little r hat to mean the traditional radial unit vector pointing away from the center. And using, and big R is the actual distance. R vector is from my differential to the center, which is where I'm trying to find my magnetic field. Worst case scenario is I'm going to be off by a negative sign at the end. And if I am, I will say it's probably not the last time I'm off by a negative sign at the end. Oh, that is the vector there. All right, so let's simplify this. So I got mu naught I over 4 pi. Negative r squared d theta. And then I'm left with this theta hat cross r hat over r cubed. That cancels out with 2 of those. So what is theta hat cross r hat?
S hat.
What's the direction of r hat?
Outside.
Okay, so in this particular situation right there, r hat, it is towards the outside, is that way, that's r hat. What's the direction of theta hat? At that point,
Would it be perpendicular?
it would be going which way?
This way.
Out.
That way. Wait, perpendicular from.
So I have, so looking at my circle there, looking at that as my differential, little r hat is pointing that way.
Theta's over there.
Yeah, theta hat is pointing that way.
So it's out.
So r hat first cross theta hat
So it's pointing in.
would be in the k direction. K hat.
Oh, theta. Wait. Would it not be out in the board? Because it's theta cross r hat, or am I just?
Oh, wait a second. Theta hat cross r hat, that would be in the board. And so ds, that's r theta. Oh, yes, you're absolutely right. It is in this board. Because theta hat's that way, r hat's this way, theta hat comes first, so theta hat cross r hat into the board. I was trying to force make sure we get a positive answer here, but I got a negative right there I need to get rid of. So that will be negative mu sub naught I over 4 pi d theta negative k hat over big R. So we end up with B being, well, we'll pull the constants out, mu naught I over 4 pi R times the integral of k hat, integral of d theta. As I go around the loop, that's going to be equal to 2 pi. So I'm left with mu naught I over 2r k hat. Now, one of the reasons I wanted to go through that is, if we look at our 2 equations there, if I have a long straight line, that the magnetic field has a 2 pi r in the bottom, in the denominator. If I have a circle of wire, it's just 2r, the pi is gone. Students in a panic in the past have looked at it and they think circle of wire, oh, circle, 2 pi r, and they shoot for this equation. When this 2 pi r is describing the line of magnetic field, it's not describing the geometry of the wire. So just be aware of that. If I have a long wire at 2 pi r in the base, if I have a circle of wire, there's no pi.
Is there a conceptual reason for that? Why?
Because we're finding the magnetic field, this comes from the geometry of the magnetic field, not the geometry of the wire.
But that comes from the geometry of the wire too, or something.
So conceptually, that's why I can argue that one. Conceptually, this one, you can make a conceptual argument that since all of the wire are the same distance away, whereas here, this R is the closest point, whereas that one, the radius is the same distance from everything, you get a larger value. So that would be a conceptual argument for that. The specifics of why not pi, I'm not really sure I can come up with a conceptual reason other than it's the way the math worked out.
No, that's fine. There's, you equate pi with circles a lot of times, and you have one with a line, and you don't have one with a circle, so.
Yeah.
But also with the circle, you equate 2 pi, and you still have the 2 there, even though the pi is gone, so that messes with my mind a little bit too.
If it does, correct. Because usually there's plenty of time for that, right? Questions up to here?
Oh, but I guess you did, you had a 4 pi before, and then you took out 2 pi, right?
Yeah.
So you still have a 2.
I don't get how do they need theta, then theta hat, where did the theta hat?
When you're dealing with R hat, so I hat, J hat, K hat, nice rectangular coordinate system. When you're dealing with a polar coordinate system, ultimately, we need a magnitude and direction. So if I take that vector right there, the magnitude is going to be length r. And so r hat as a radial unit vector is always away from whatever the center is. There's also an angle here, and the way the math people have worked it is that positive angles go in counterclockwise direction. And so theta hat, so r hat goes in that direction, theta hat goes in that direction. It's just, that's what they decided.
Then you multiply them.
So when you do theta hat versus r, cross r hat, so theta hat, cross r hat, theta hat's in that direction, r hat is that way, so fingers curl, thumb points into the board.
Well, it's nice that they somehow aren't given in rectangular coordinates and you have to convert to polar coordinates, like calculus, but.
Yeah,
It
we
seems
are
like
taking
already
advantage.
set up for polar, which is nice.
We are taking advantage of the work that the math people did. Okay. Other questions? Okay, so great, we can find out the magnetic field. I just gave you the configuration. If it's a finite wire instead of an infinite wire, then, well, the limits of integration change, but other than that, it's the same process. But if I have a magnetic field, how does that affect a charge? So this is how a charge affects a magnetic field, but how does a magnetic field affect a charge? More right angles. I think we can safely say this is the third physics equation of the course. So if I have a charge that is moving at a velocity v in a magnetic field v, then this is the force that's applied to it. So first let's just work on directions. Don't worry about the computation quite yet. This is a magnetic field coming out at us. As the magnetic field is coming out at us, I'm gonna take a proton and I'm gonna shoot it into the field. In which direction, when that proton enters the magnetic field, in which direction will it be forced? Well, proton is positive, so Q is a positive number. So the direction is gonna be whatever V cross B is. V is that way, to the right. B is coming out, so V cross B points downwards, and so this will be forced down.
Now, the particular path in which it takes is gonna be more like that.
No, but, well, maybe, depends upon part of your reading of your hand gesture.
Like, as it enters, it's gonna be slowly pushed downwards? Or is it gonna be?
It depends on the strength of the charge, its velocity of the magnetic field.
Gotcha.
Alright, so it's going to be pushed perpendicular to where it's going, so then it'll be traveling, say, in that direction. Matter of fact, the force is going to be perpendicular to the velocity the entire time, because cross products produce a vector which is perpendicular to the force. So what do we have if the force is perpendicular to the velocity? What type of motion is that? Flashing back to 251. Shit. Torque.
Rotational motion.
Yeah, we could be more specific than that. If you were, do some basics here. I have a particle I have some object traveling this direction. If I apply a force in the direction that it is moving, what's gonna happen to it? Well, if I have a force applied to it, it's gonna accelerate. Let's be more specific.
Accelerate in the same direction.
Which means, if you're driving a car, what are the three accelerators?
The
There-
steering wheel, the gas pedal, and then
Friction of
the brakes.
Yeah, there's some internal friction I wasn't worried about. But as a driver, you have access to automatic transmission for those who want to go that route. Steering wheel, brake, and gas pedal are all accelerators. Remember, acceleration in physics means it's speeding up, slowing down, and or changing direction. So, of those three, if I put a force in the direction of motion, what will happen to it?
Its velocity increases in the direction.
Okay, I heard what the answer I was looking for back there.
Speeding up.
Speeding up. That's what I was looking for.
The velocity increases the same thing.
If it's going this way and you apply a force opposite direction,
Slowing down.
and if you push perpendicular to the motion,
Change direction.
okay, just changing direction. So if I have an object that's not changing magnitude of its speed, magnitude of the velocity or the speed. If the speed is constant, but the direction is constantly changing, what's happening to this object? Well, you say spinning, I picture that you suddenly get the proton to be doing this as it's moving.
Not spinning, but it's traveling in a circle.
Yes, otherwise known as,
centripetal.
thank you, centripetal motion. So what's gonna happen is that it's gonna start to travel in a circle. Now, potentially if the magnetic field's strong enough, it's gonna actually curl all the way around. This is the part with the hand gesture. Will it do that? Well, only if it's part of a larger circle. That's supposed to be a circle.
First circle ever.
Don't worry, I'll draw worse. So this actually is an incredibly powerful thing here. Because what happens if I shoot an electron? We'll go for green for that one. If I shoot an electron into the same magnetic field, then D would go the other direction. V cross B is still the same, but Q is negative, which means the opposite direction. So an electron would do this. So first off, if I have a particle collision, so You zip up a bunch of protons, slam it into some carbon or some target, you get a shower of particles coming out. If I expose it to a magnetic field, I can easily identify which are the positive charges, which are the negative charges by what happens when exposed to the magnetic field.
Do they use magnetic fields and particle accelerators to actually fling them around the track too?
Yes. A combination of magnetic fields and electric fields. All right. So let's just do a little math here. So if I've got this particle entering in, I have the velocity and the magnetic field perpendicular to each other in my scenario here. So this, the magnitude of the force, it would just be QVB. If it is traveling in a circular orbit, well, you've gone through the process. I got a particle here. I have a magnetic force pointing towards the center. There's my force diagram. Direction of acceleration. We're going through facades.
Centripetal.
Yep. So I have a particle here at this point. The force is pointing towards the center there. F sub D, or in whichever one you prefer. Direction of acceleration is that way. Coordinate axes. What do you want to make the positive direction? Up.
The iPad would be in the same direction as the force.
I would recommend setting the positive direction to be in the direction of the force.
Yeah.
Or the acceleration. All right. We don't have, it's a one-dimensional problem. If I'm taking a snapshot in time, it's a one-dimensional problem. I don't have to use I hat, J hat. So that's pointing this way. Coordinate axis, I don't need to break it up. Decomposition's done. Equations of motion. F equals,
MA.
so this be equal to mass times acceleration, centripetal. Formula for centripetal acceleration, or magnitude of,
V squared.
just the acceleration piece.
B squared over R.
That's the one. Yeah, M only shows up when you're looking for the force. So that's equal to mv squared over r, or, really stretch the memory there. What's the other formula for magnitude of centripetal acceleration besides v squared over r? See if I can go back, get this sausage and change your grades.
You use them for one semester, it's like, it's not gonna like stick completely forever.
V is equal to omega r, so v squared over r would be omega squared, r squared over r, or omega squared over r. So, instead of v squared over r, you could have done it omega squared r. Sorry, I know you were looking for it.
I did indeed found it.
Okay. So we're now dealing with, if I have a magnetic field going perpendicular to the particle's velocity, that the magnet, I have this QVB equals mv squared over r. V cancels out, one of them does. Ultimately, magnetic field is something that I control. I want to get Q and M together, so I'm going to Q divided by M is equal to V over the R. Let's make sure that that works. Okay. The power of this is that the charge, I can have different charges, some multiple of the charge of an electron or proton. Masses are relatively unique. If I shoot a bunch of particles into this magnetic field, from which way it goes, I can determine if it's positive or negative. I can now, if I can measure that radius of curvature, and I control the magnetic field and I know how fast it's going, I can do a pretty good job of narrowing down what the particle actually is. And so we get into particle identification.
That's cool.
Now the difficult part, the really difficult part. Yeah, we can control V. I have some sensor here, I have some sensor here, time how long it takes to get from one to the other. But really in a high energy experiment, you've got millions of particles. You're slamming a proton into, at least the one I was working on, into some sort of, it was carbon, some sort of carbon target. And you get millions of things coming out of it. So you have to sort of piece it together. So in reality, you've got a bunch of detectors here, and this will ping, and this will ping, and this will ping, and you get some sense that there's a particle going like that, except for the fact that in reality, you've got a whole bunch of particles. You're getting a whole lot of places where you know that a particle has been, and then you have to sort of figure out what's the best bet for which. So it hit, a particle hit there, but did it hit there next, or hit there next, or where did it hit next?
Can the computers separate out the path based on like the concentration of mass in one particular area on each sensor or something and let it?
Yeah,
follow?
the process, for the project that I was on, the processing of doing particle identification took pretty solid 2 or 3 months of computing power.
Did you use a supercomputer?
Fermilab, I'm guessing yes, but I don't know for sure.
You were at Fermilab doing this?
Yes and no. The project was at Fermilab. I have been to Fermilab.
Nice.
I was not at Fermilab at the time that the experiment was actually being done. When I went to Fermilab, I was with some people from University of Mississippi who were also part of the project, and they came in and started basically scavenging the machine. I mean, legitimately, we did that part. We did that part. Let's make sure we take those. Cool. And then they took all the cobwebs. So we were- Questions? I have no idea what time it is. We have 6 minutes.